Antiderivatives. Let's think of the word anti on the front of derivative. Anti typically means inverse or opposite of something. And what this is going to require us to do is to think backwards. We do this to you often in math. First we taught you how to add, and then we had you subtract. Taught you how to multiply, then we had you divide. Taught you how to FOIL, multiply two binomials together. Then we had you factor. Well, taught you how to find derivatives or differentiate, and now we want to think backwards, find the antiderivative, or what you started with and then you ended up with this derivative. So an antiderivative, if we have a function capital F, it is an antiderivative of little function f on an interval I, provided the derivative capital F prime of x equals little f of x for all x on I. So this just simply gives us a definition for antiderivative, and it just says it's an antiderivative if you take its derivative and you get this function little f of x. So we're thinking backwards here. Here is a function and it's 1. Well, it's what I got when I took the derivative of some capital F of x. So what was capital F of x? So when I took the derivative, I got 1. Well, we can see that if we had capital F of x equal x, when we did its derivative, we would get 1. The derivative of x is 1. What if I took the derivative of some function and I got 2x? What was the function? So thinking backwards, well, that function would have been x squared, because if we did a power rule, power out in front, that's 2, decrease the power by 1, it would look like that. I took the derivative of some function and I got cosine x. What was the function? And we know that if we started with sine x and we took a derivative, we would get cosine x. Here's a little trickier one. I took the derivative of some function and I got 1 over x plus 2e to the 2x. What was my function? So we've got to think backwards here and say, if I had a function and I took a derivative and I got 1 over x, we're going to do this in pieces because we know we can differentiate term by term. So we will go ahead and think of the antiderivative term by term. So I got 1 over x. Okay, well that must have been natural log of x then. Plus, now I took a derivative and I got 2e to the 2x. Well, first of all, we know that if we did derivatives of e to the 2x, we'd get e to the 2x's, so that would have an e to the 2x on it. But what about the 2? Oh, that was generated from the chain rule. So the function I differentiated was e to the 2x, because the derivative of e to the 2x is e to the 2x times the derivative of the stuff here, the 2x, and that's where this 2 came from. Now, each of these answers I gave is an antiderivative of the original function. However, I didn't list all of the antiderivatives. Because, for example, what if this first one here, instead of being x, what if it would have been x plus 3? And I took the derivative here. Well, that would still give me 1 because the derivative of constant is 0. This x squared could have been x squared plus 4, or it could have been x squared minus 3, or it could have been x squared plus 1, or it could have just been x squared. Any of those have a derivative of 2x because the derivatives of constants are 0. So how did I know there wasn't a constant on the end of any of these? So as we go to do antiderivatives, we won't get just one solution. If we're looking for all antiderivatives, we would get a whole family. Let's look at this example. So this function whose derivative is 2x. Well, it could be x squared or x squared plus or minus some constant on the end. So it is a whole family of solutions, and this is graphically showing you that every one of these curves has a derivative of 2x. And the reason why, if you think of the derivative as the slope of the tangent to the curve, and if we plotted what was going on here with this tangent here versus here versus here versus here versus here and so forth, if I did this on this next curve that was just a vertical translate of the other curve, I would get the very same slopes. And you could see that would be true for any of these curves. Anything that was an x squared with some kind of a vertical shift would still have the same tangent slopes as you moved along the curve, because it's a rigid transformation. We didn't change the curve other than moving it up or down. So following a tangent line, we would get the same slopes everywhere. So if we wanted to express all antiderivatives, of the function 2x, we would need to express this with a plus c on the end. It could be any constant on the end. So if f is an antiderivative of little f on an interval I, then the most general antiderivative of f on I is f of x plus c, where c is an arbitrary constant. Now we could be specific and give us what's called an initial condition so that we could identify what the c might be. So this one says find the antiderivative of f of x equal cosine x that satisfies, and this is called an initial condition. It's giving us a point on the curve. So if we went to find the solution to this, we say, well, let's see what function has a derivative of cosine x. That's sine x, but it could be plus some constant. And then we could determine what it would be by using this initial condition. So we could put 0 in, and that would be the sine of 0 plus c, and set that equal to 1. So that would let us know that c, since sine of 0 is 0, c would need to equal 1. So we have a specific answer to this. It is just one specific antiderivative because it is the antiderivative that passes through our given point, so we meet our initial value or initial condition. Now here are a bunch of graphs that have the same derivative. They all have a derivative of cosine x, but it is only the blue graph that satisfies f of 0 equals 1. So the solution here is sine x plus 1. An indefinite integral is defined as an integral of f of x dx equaling capital F of x, where the derivative of capital F of x equals f of x. And what it equals is an antiderivative of this little f of x function. So if I wanted the integral of x to the fourth dx, then I would think of this as, what is an antiderivative of x to the fourth? Well, that would be 1 higher power, that's x to the fifth, but then we need to put it over that power so that if we move the power out in front, those would cancel and then decrease the power by 1. It would look just like that. But wait a minute, what if there was a plus 2 on the end of there? If I took the derivative of this, I would have x to the fourth because the derivative of a constant is 0. But wait a minute, what if it was x to the fifth over 5 minus 3? Well, if I took the derivative of this, I would again get this. So there's an infinite number of answers to finding this antiderivative. We know that they differ by a constant. So if we want to find the most general antiderivative, we'd put a plus c. So for an integral, we want to list all possible antiderivatives. So we want to list this as x to the fifth over 5 plus c. Let's look at the properties of indefinite integrals. So if we have a constant, we can move it out in front and we can go ahead and integrate the function and then multiply the constant. If we have the integral of a sum, that equals the sum of the two integrals. And so let's see if we can compute some various indefinite integrals. If we want to integrate k, we know that's going to be kx plus our constant of integration. If we're looking at the integral of x to the n, that's essentially the power rule in reverse, so it would have been 1 higher power, but we need to divide that by that power, so over n plus 1, so that we could see if we, it's always easy to check this because you're better at differentiation than finding antiderivatives, so do a quick derivative and make sure you get this back again. Power out in front, those powers cancel, decrease the power by 1. Looking at the integral of 1 over x, we're looking for an antiderivative of 1 over x. So what function's derivative is 1 over x? And that's the natural log. We need absolute value on the x plus our constant of integration. Looking for an antiderivative, so we get e to the x, and that's just going to be e to the x plus a constant. If we're integrating a to the x, if we remember, if we differentiate a to the x, we get a to the x times the natural log of a, but I don't see any natural log of a here, so if we're doing the antiderivative, we're going to need the a to the x, and we're going to need to divide by that natural log of a. Looking at some more, if we integrate sine x dx, we're looking for the function whose derivative is sine x, and that would be negative cosine x plus our constant of integration. Over here, function whose derivative is cosine x, and that would be sine x plus our constant of integration. A function whose derivative is secant squared x, and that would be tangent x plus our constant of integration. The function whose derivative is cosecant squared x, that would be negative cotangent of x plus a constant. The function whose derivative is secant x tangent x, and we know that would be secant x and then plus our constant of integration. Cosecant x cotangent x, if we integrate that, the function would be negative cosecant x plus a constant. Looking for the function whose derivative is 1 over x squared plus 1, and that's inverse tangent, and then of course we need our constant. And then lastly, the function whose derivative is 1 over square root of 1 minus x squared, and that is inverse sine.